Let's talk about section 12.3. Now with section 12.3, I do want to point out this is regression analysis. Many of you guys will probably, unless you're a science major, may never see this. So you will notice that this section has been deemed a bonus section for the homework, and I will not include it on the Unit 5 exam. However, it is a great section to go over and learn a few things if you are looking at a regression style analysis, especially for my science majors. Now understand that one important thing that we have to discuss is that the regression line, or also known as that line of best fit that we calculated in the previous section, is a sample statistic. Because it results from calculations performed on a sample of the population's data, a true regression line would only come from a census of the entire population. That does mean that there's variables, there's slopes, there's y-intercepts. It contained in it all of that information from the population parameters. So since we represent true regression lines using Greek letters, we will basically use for the most population parameters, if I'm talking in terms of a population, I will say y equals beta null plus beta sub 1 times x, and that's my population parameter. Whereas when I do statistics there, it's y hat equals b sub naught plus b sub 1 times x. And again, y represents the actual value that occurred in the population, so the real data, and y sub hat is going to be that predicted value based upon the sample data that we might have. As we expect, these two values are normally not the exact same. Okay, so since they're not normally the same, we have this item called residual. A residual is the difference between the actual value of y coming from the original data and what would be the predicted value of y hat found using the regression line. Okay, now it's very nice and easy to get a residual. It's literally you take that y value minus the predicted y value. Okay, now the predicted y value is going to have to come from the best fit line, or also known as the least squares regression model. So let's take a look at this. So the following data from a local school district of children's ages X and reading levels Y for these data, a reading level of 4.3 would indicate that a child's reading level is 3/10 of a year through 4th grade. Okay, now that does mean that the children's ages are given in years here. So if I have X being my ages, so I've got like 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and the reading level being 1.3, 2.1, 3.7. Now do notice that as I begin to look at this, I do kind of notice that there is a bit of a regression of increasing values in my y as my x's are increasing. So I'm going to suggest that there is some type of relationship to this. And since it does look like there could be a possible relationship to this, let's go ahead and see if it's a linear regression. So let's run a linear model. So using a TI 83 or 84 plus graphing calculator to determine the linear regression model there, we can calculate the regression line is y hat equals a negative 3.811 plus 0.865x. We do note that r is 0.989, which again is greater than what the critical value is for a 5% level of significance. And again, that is going to come from our critical value here. Guys, do be aware that this part right here is going to come from R sub alpha is from a table. So you have to go look these up on that critical value table and compare that critical value to the R you get from the calculator. And as long as this R is bigger, you're good to go. It does mean that this is significant enough. In our case here, anything that's normally 0.9 or something, it should be significant enough, but it does depend on what that level of significance that we have, that alpha, as well as how many data values we might have. Okay, so furthermore, the following scatter plot depicts this linear pattern of the data values. So on the next page, I'm going to show you what the plot looks like. And here's the line that's going to predict what the linear regression model kind of follows along if I was to use it to make predictions. So here we have our regression itself. This is just a stat plot, okay? And using the regression equation to calculate the estimated y hats for every single x value. So instead of x equals 6 and getting the value that we had, we're going to plug in x equals 6 into our model and see what value it comes back out with. Okay, so to do this, it's actually not as hard as it looks like. So what you can do is in your TI 8384 graphing calculator, you can go to Stat and Edit, and in list 1 should be all the ages that we had, the x values, and list 2 is all the reading values. So I'm going to use the arrow key and I'm going to arrow over to list 3. Now when you arrow over to list 3, arrow up and highlight list 3 itself, and then you're going to enter in the following formula. Now this formula should look a little familiar because this literally was the formula we got for y hat. It's just we are now plugging in those values, and then you're going to say times list 1. Now that's going to be where a lot of people make a little bit of an issue, and so I want to show you where to get that. Okay, so you should see a calculator up on the screen, and again I just want to remind everybody of what is actually being done. And so you have everything in list 1 and list 2 here, and then you just did stat, calculate, and you went to number 4, linreg, okay, and we said list 1 and list 2 is what we were looking at, and then we're going to say calculate here. Okay, now again, this is where you get your a times x plus b, and again, there it is right there. Again, there's that b value, there's that a value. Now what I'm going to do is I'm going to take that and I'm going to say stat edit. I'm going to arrow over to list 3 and I'm going to move up and highlight list 3. Okay, so you notice I'm highlighting the name here, and I'm going to just hit enter, so like it's going to basically say list 3 equals, and I'm going to type in the formula. So this formula was negative 3.811 plus 0.865 times x. Now the thing is I'm not going to multiply by x. I want to know what those actual x values are. So I'm going to say list 1 here. Now if you hit second L1, that is going to pop in your list 1. Okay, and there we go, and hit enter, and it basically, it's like an Excel spreadsheet. So if you've ever used an Excel spreadsheet, we're kind of doing the exact same thing. Now you can do the exact same thing in Excel if you would like to do this as well using Excel. Okay, and now what I'm going to do is I'm going to arrow over to list 4, and I'm going to move up and highlight list 4. And again, the whole goal is to figure out what that residual is. So looking at, these are the true y values and these are the predicted y values using the formula. And so again, I'm just going to hit enter. So now it's fully highlighted, and I'm going to say list 2. So notice second 2, above it is the L2, minus second 3, giving me all the list 3. And so basically anything in this column is going to be this minus this. And there we have it. Okay, now again, I'm going to move into this where you see it a little bit nicer and bigger. So again, this was everything in list 1. This was everything in list 2. This here was after we created our regression model. We said, okay, take that regression model and replace all those x's with these numbers here to figure out what does the model predict them to be. And then here was, we want to know what those residual were, which is basically take the original y values from the data and what the predicted y values, and how close is it in that prediction. Okay. Now the residual of each value reflects basically how far the original data point is from the point of the regression line. Basically, graphically, it's what we call the residual is like a vertical distance, meaning like how far away is it above or below, okay, and from that regression line. So if we actually graph the regression line on a scatter plot of data, we can draw vertical bars and find that distance between each one of those points. So it would look something like this. And again, notice that when we were looking at these, we were able to see kind of what that distance was. Some of them were closer than others. Some of them were a little bit further away. And again, this is where it's a little nice to take a peek at it. So again, this is where, and I had the first one was negative, which again, it looks like it's a little below. The second one was also negative, but it was below, but just barely, so a little bit smaller. And notice on the third one, it was above. So again, it's above it. It's a positive number here. And notice on some of them, the closer we get, like it's really just not that far off. Notice that 1, 2, 3, 4, and 5 here are really, really close. Like they both look like they fall on the line, but it's not a perfect fit. And you can notice here that these ones are really, really close to the line, but they're not perfectly on it. They're just slightly off. Nothing is a perfect fit, okay? Okay, so now that we've talked about residuals, now we need to talk about the SSE. Now, the SSE stands for the sum of the squared errors. Now, SSE, now this is a capital SSE for a regression line, is the sum of the squares of those residuals given by the following formula. It's y minus y hat. Take that and square it, and you add them all up. Okay. Now, this basically is, it's called the sum of the square of the errors. To interpret the sum of the square of errors, it's considered the size of the value of the SSE. If the data points are very far from the regression line, the SSE will be really, really large. And if the data points are actually really close to that regression line, that SSE will be relatively small. Please understand that the larger the value, the SSE, the worse the linear model actually is at being able to predict the value of y itself. And the smaller the value of the SSE, the better that linear model will be at predicting. And the line that fits the data the best would be the one that actually has the smallest SSE. So to calculate the sum of the square errors, so the SSE, for the data of these children's models, we're going to have to use what we've done in previous things. So the first thing is you're going to be using the values that we calculated in the previous example, and you're going to start by beginning squaring them. Now, you've already kind of done this a little bit, which is really nice. So you've got all of those items right there, and we're going to just square them. Okay. Now, again, this works really, really well in Excel files. It can work in a calculator really, really well, but I would suggest for this section, you might want to open up and use Excel. For those of y'all that are maybe not as familiar with it, do remind yourself that you do actually have full access to Excel using the school's resources. You actually can even download it yourself for free because you are a student at CCGA, okay? You can use a calculator as well. I would highly suggest maybe convert to Microsoft Excel just for this section because it is a little bit easier to deal with, okay? Once you've got those residuals and you've squared it, okay, you're going to add them all up. Okay, so I do want to show you how you can use your calculator to help you out with this, but again, I do highly recommend use Excel. Excel will be a little bit nicer. It does take a lot more steps if you're not using Excel. So to help you out here in the calculator, you've already got list 1, list 2. Here's my list 3. Here's my list 4, which was basically the residuals, okay? Now we just need to take it and square it. So I'm going to highlight list 5 and I'm going to say I want to take, so enter, make sure that it's got a blinky cursor there so I can type in, and I'm going to say I want to take list 4 and square all of those. And hit enter, and then it automatically squares them all. Now again, the calculator only has so much room to show everything, so like if you'll notice that this number is exactly what I have here, okay? So they are exactly the same number, it's just it doesn't all show up in this really small area. Now I need to sum all of them up, so I need to add all of these together. And again, how to do this is in your calculator, you're gonna have to say, okay, it's list 5 that I'm trying to sum here, so please be aware, I'm trying to sum list 5. I'm going to go to stat, I'm going to arrow over to calculate, and then I'm going to run a 1-bar stat, and I'm going to say list 5. Okay, and again, second 5 puts in list 5 there, and then I'm going to say calculate. And again, if you'll notice there, it says sum of all the values of x's, which again, this, even though they're technically y's, the calculator assumes that anything put in is an automatic x here. So the sum of all those x's, and there it is, that 1.394. Okay, so just so you guys know that that's where it is, and just in case you need to do it a little bit further there. For those of y'all that have the TI-83, remember, you don't have that beautiful pop-up menu, so you just have to tell it that it's a 1-bar stat and you want it to run it on list 5. So make sure that when it says 1-bar stat here, and then actually type in list 5 and then enter, and you'll get the same thing. Okay, and there you have it, and that's the nice part about it. And now you have what approximately your SSE is. And I say approximately because, again, we are going to round it, and you're going to round it to so many parts. Now, once you have that, what's really cool about that is that now we can actually figure out what since we have the SSE, we can use the SSE to actually, again, this is the sum of the square errors. And again, if I have the sum of the square errors, I can use this to calculate my standard error for the estimate. Now the standard error for the estimate, again, standard error is just another fancy way of saying a standard deviation, because that's what a standard error is, but it's a standard deviation of the estimate. So the standard error of the estimate, which is measured by the following formula. And it again is basically the square root of the SSE, which that formula there is the SSE divided by n minus 2. Okay. Now, where you have basically all of this here, again, n being that total number, but again, you're going to have to figure out what your regression model is. So in our case here, to calculate the standard error for that estimate of data on children's ages, again, this is the SSE. This is needed first if you're going to do it by hand. There is a way to get the standard error of the estimate, which is not the SSE. The standard error can be done using the calculator. Okay, so to kind of help you guys out, again, remember, I'm telling you, there's a lot of stuff in the calculator that can be done, but some of it does involve a little bit of extra stuff, and this is a section that involves a lot. So you're going to start by putting all of this in the calculator. Okay, so stat, edit. Now, again, this is all in list 1 and list 2. Remember, list 3, 4, and 5 we created just to be able to get our SSE. Now, to get your standard error of estimate, so the actual standard deviation of the estimate, that's basically what this is we've got all of our data in list 1 and list 2, and then we're going to hit stat, arrow over to test, and then I want you to scroll down and choose option where it says LinReg t-test, which should be option F for most people. Okay. Okay, now once you've selected that, it will ask you where is all the data. And again, my main part of the data, my X and Y list, that's all I want. I don't want it to look at list 3, 4, and 5, is going to be in list 1 and list 2. And then we're going to determine basically what that alternative was. And our basic one here is we're just going to say the not equal. It doesn't actually matter right now because we're not running the test itself. Okay. It should automatically populate reg equa into Y1, and what that does is that's going to put that prediction model in Y1 straight away for us, which is a little nice, and then just go down and click calculate. Okay, so one more time, so those are your steps. to get to the Lin-Reg t-test. But again, you have to start by put all the stuff in the calculator first, stat, test, and then hit this, okay? Be sure that when you are doing the Lin-Reg t-test that it does know that the X list is in list 1 and the Y list is in list 2. The entered value for your frequency should just be 1. Again, we're not looking at multiple variables right now. Okay, we're going to choose the alternative hypothesis to basically be not equal to 0, meaning that there's some type of significance. Again, we're not really running the actual test. I just need to know what the standard deviation is of this error estimate, but I need it to do the Lin-Reg standard deviation and not just a normal standard deviation, okay, which means it has to calculate out what that SSE is. And then you're going to choose calculate and enter. Okay, now the results in the following screenshots are going to show what is included. And now you're going to see a test statistic. You're going to see the linear relationship between everything. You're going to be given that y equals ax plus b. Sorry, this one gives y equals a plus bx, sorry. Where a is going to be the slope and y-intercept, those letters A and B are. So you're going to get that regression line for the same thing. It's a little opposite of what we were used to seeing. You were used to seeing Lin-Reg AX plus B, and they basically just switched the pattern. But again, you will see this formula written, so just be aware, note what the formula is in the problem. It will also give you what the degrees of freedom are. It will also give the p-value for the hypothesis test. Now this is saying that you've actually chosen the correct hypothesis test. So be aware of that. If you haven't chosen the actual correct one that you're running, then that might change what that p-value is. But for the most part, we're not really concentrated on the p-value itself. Okay. You're also going to notice that there is going to be a little bit of a down arrow there. And again, the down arrow is where I really want to pay attention to. The last two values that are given, when you hit the down arrow, you're going to see S, R squared, and R. R is that correlation coefficient that we've talked about previously. But the S, that third to the last, that S, that is the standard error of the estimate. Okay, so that is going to be what we're actually looking for. Again, this is the standard error. This is not the SSE, so be aware of that. So the standard error of estimate for the data that we have on the ages and reading levels, also denoted by the S sub E, was approximately 0.417. And since this value is actually close to 0, we can also conclude here that the data points do not deviate very much from the regression line at all. Okay, so let's talk about the prediction interval. Now, a prediction interval is a confidence interval for any individual value in response to our variable of what we have for y, given that the value for our x value is fixed. Okay, now again, a prediction interval meaning I've got a low bound and an upper bound based upon that prediction. Now, to get that, this is a very crazy looking formula, and I'm just going to point it out there. It is a little crazy, so be aware that the margin of error of a prediction interval for an individual value of a response variable y is given by the following, and it's going to be your E is going to be your T alpha over 2 times your standard error of estimate, so the S sub E there, times a square root of 1 plus 1 over n plus n times x sub 0 minus x sub bar, quantity squared, all over n times the sum of the x squareds, the individual x's squared, and then add them all up minus the sum of all the individual x's, and then that answer squared. And again, that's all underneath the square root. It is a really crazy looking formula, so be aware of this. Okay. Do remember the T alpha over 2 we've looked at before. That is that critical value. You are going to need to know your confidence interval here, which is again going to be 1 minus your alpha. Your degrees of freedom, again, because we are looking at a linear regression, that means my degrees of freedom here are going to be n minus 2. It's a little different than what we are used to, so be aware of that. Okay, again, S sub E is going to be that nice, lovely standard error of estimate. But again, remember, you need the SSE to get this, or you're going to use the calculator to help you out there. And N is the number of data pairs in the sample itself. Okay, now there's a couple other symbols there, so let's talk about them. X sub 0 is the fixed value for the explanatory variable, so that independent variable. And then X bar is the mean of all the X values from the data point itself. And then X sub I is the ith value. Ith value sounds a little weird, but basically it's the individual data value in the independent data for the X's. Okay. Now, the prediction interval for an individual value that you might see here. Ooh, sorry, went too far. The prediction interval for the individual value of your response variable y is basically, you kind of need to know what your y hat is, and then you're going to need to add and subtract out what that e is. Okay, so you need that margin of error. So here we go. And again, I'm going to walk you guys through this. So we're going to construct a 95% prediction interval for the reading level of a child who is 8 years old, whose data from this example of our children's age here is as follows. Again, now do notice I said that the reading level of a child who is 8 years old, so I'm focusing on this one here, but I do need all of the data to begin with. So again, I'm focusing on this one here. Okay, so I am going to put in this that neither a TI-83 or 84 Plus graphing calculator nor Microsoft Excel will directly calculate the prediction interval for one item. So we must calculate the margin of error by hand and using this value to construct the prediction interval itself. Okay, so first thing you're going to have to do, now again, we can use the calculator to help us work a little bit, but it's not going to directly give me exactly what it is. So step one, find your regression equation. Okay, and we've known this from previous examples, so I'm just going to pull this out. So again, we've done this already. I do want to make a small note. There are many stat softwares out there. Minitab is probably the only one that I know that will directly calculate a prediction interval, so just be aware of that. Okay. Now, step two is you're going to use the regression equation to calculate out your y hat for the given value there. And again, that's going to be the one, for example, we want kind of x equals 8. So we're going to go with our model and plug in 8 for x, and we get our y value to be 3.109. Okay, and again, this is my y hat for when x equals 8 itself. Okay, now we can use our calculator to help us get the sample statistics necessary for part of it for the margin of error. Okay, and to do that, we can kind of get all the little things that we're going to need. So using a TI-8384 graphing calculator, we can enter in the ages in list 1 and we can enter in the ages in list 2, and then we can say stat, arrow to calculate, and now here's, you got to be careful here. Now you're going to run option 2, which is a 2var stat. Now this is going to give the many different things I actually need for the items here. Okay, so I need what x bar was, I need the sum of the x sub i's, I need the sum of the x squareds, and I need what n was. Okay, now again, this all comes from a 2var stat, and just make note of all of that information, put it in there, and write it down. Okay, now you're going to recall that from a previous example, we did actually get our S sub E, which was this number here. Again, make sure you take more decimals than you think. About 6 is the minimum I would suggest using. And again, this was also found using the graphing calculator running that LINRAG t-test. Now, lastly, the last thing you're going to need is that critical value. You can use a table for the critical value. Those of y'all that have a TI-83, you will have to use the table. For those of y'all that have a TI-84, you can actually use the calculator to get this. And again, remember that this was basically inverse t, and then you're just going to say 1 minus alpha over 2 and put your degrees of freedom as being 8. Again, my degrees of freedom on this one is 8 because we're talking about a model, a linear model. Okay, and then you're going to find your margin of error, and you're going to substitute all of that into the formula that we just figured out. Okay, and you get it to be approximately equal to a 1.043793. Okay, so from here, now all you have to do to create your actual margin is, now that you have your error of margin, you are going to subtract the margin of error and add it. So you should have two numbers here from the original y hat that we got, that we were predicting from 8. So the lower endpoint is going to be the y hat minus my e, so that 3.109 minus my margin of error, which is approximately 2.065. And again, we do the upper point is going to be that y hat plus e, which is that 3.109 plus 1.043793, which approximately equals 4.153. Again, you can say this in two different ways. So thus there's a 95% confidence interval for the individual y value, ranges anywhere between 2.065 to 4.153. You can write that confidence interval using mathematical inequality symbols or in interval notation. And again, this is only for the 8-year-old child. So please be aware that the 8-year-old child, to be 95% confident he or she will have a reading level, will be between these numbers. Okay? This has no effect for a 9-year-old or a 10-year-old. Okay, so just be aware of that. Like, that kind of throws a couple of people off when they think about it. It's just only for the 8-year-old that the 8-year-old is going to have a reading level anywhere between that 2.065, which is 2nd grade level, to a 4.153, which is about 4th grade level. All right, so let's try this again, and let's construct a 95% confidence interval for the slope, okay, and the y-intercept. Now, the regression equations for your slope and y-intercept, again, using the data that we've had, again, we're repeating the same things here. Now, for this one here, it would be really helpful to use a Microsoft Excel. So again, this is why I said Microsoft Excel is kind of really nice and awesome with all of this. Your calculator will be helpful, but there's some things that I'm just going to say Excel is going to be a little bit better at. Okay, so in list 1, I'm going to have all the ages, and list 2 will have all the reading levels. Okay, now Excel, just like when we do in our calculator, we say stat and we arrow over to calculate or the testing. Under Excel, there's an area that says a data tab. If you will choose data analysis and select regression from the options, and enter in the necessary information for the regressions from the following menu as shown here, and then click OK, you'll be really good. Now you'll notice that I am saying here, this is basically all the X's and these are all the Y's. Again, make sure that you say include the labels, because that's really important, and then say confidence level. Okay, and we're just going to input them in saying, our summary output being in A15 here. Again, I say A15 because again, all my data X values were between A1 and A11. And again, I'm going to go back a slide just so you guys can see this. Again, A1 to A11. So you're selecting this. So click, select, and hold down and scroll. And then same thing for the B levels. So that's what you're doing there. Once you click OK, this is what's going to look like, and these are the results shown from the following screenshots. They provide an abundance of information, much of which we've discussed throughout this entire chapter, and there's just so much that you can see there. The first thing you can see is number one, the multiple R. That is basically the absolute value of the correlation coefficient. That's what we were finding when we were doing our LinReg and my LinReg t-test, all of those R's. R squared is that coefficient of determination. Number 3 is that standard of error. If you look at number 4 there, you've got a number that should also look a little familiar. Okay. Again, I'm going to continue on so you can see. The ANOVA table is something that they'll discuss if you go further on. So for those of y'all that are going to higher level stats, or you're going into science classes that need ANOVA stuff, please go ahead and look at other chapters before heading into your science classes so you have a bit of a heads up. But you'll notice that number 4 there is the residual role of the SS column is the SSE, or the sum of the square errors. And then number 5 there is the lower 95 and upper 95%. And 6 and 7 is the coefficient column that gives the values for those coefficients for the y-intercept and the slope of the regression line. So again, I'm going to go back just a few slides so you can see all that here. And again, this is that lower and upper. Here's the coefficients, that 6 and 7. So here's the lower and upper for each one individually for the x-intercept, and this is for the ages here. Sorry, y-intercept. I should say y-intercept and not the x-intercept. Y-intercept. And again, there is that residual SSE that we were talking about. So there's, like I said, there's just so much here that you have, and Excel will do so much more all together in one. Again, we're not going too much into the ANOVA tables, but just be aware that those do come out in another section, okay? So our lower and upper endpoints for that 95% confidence interval for the y-intercepts and the slopes are given as follows. And again, as you can see with those, that row labels that the intercepts, basically you've got pretty much everything you need there. So for the y-intercept, it was between a negative 4.965 and a negative 2.67, negative 2.657. And again, we had those there. And then we also have this one here, which is for your slope, okay, and the upper and lower. This one can be done with the calculator, so be aware that the calculator will help you with this one here. But this one is not kind of really, I haven't found a good way to show it in the calculator, so if you do learn it, please let me know. But for the slope, you can do that one in the calculator, okay? And I hope you guys learned an awful lot with this linear regression analysis here. Again, we're not going to go too much further in depth in it other than this, and I will not be including it on the final or in the Unit 5 exam, but I did want to at least give you guys that heads up, especially for those of y'all that are going into psychology classes that will be using these types of numbers, as well as the science classes. They start into kind of these types of things, and you need to be able to kind of look at these numbers and see what they kind of are and maybe interpret them a little bit further, and how statistics goes further if you like to take probability and stats too.